Hello everyone, welcome. And today we're going to look at electronic configuration in AS chemistry. So, what is a key part of electronic configuration? So they're arranged in principal energy levels or quantum shells. So principal quantum shells are basically the shell numbers. So over here the innermost shell is 1, the second one is second, and the third one is third, and so on. And a principal energy level, which you can also lose, are just names for the shells. So the first one is called K, the next one is called L, and then it just keeps going on M, N, O, and P. So, and the lower the principal quantum number is, the closer you're to the shell. So here's some general information. The first shell can hold up to 2 electrons, the second shell can hold up to 8 electrons, the third can go to 18, and the last one, the fourth one, that's not the last one, can hold up to 32 shells. So, what are subshells now? The quantum shells, which we have learned about, they have subshells in them, which are denoted by the letters S, P, and D. And the energies of the subshell go in the order D is the greatest, P is less than D, and S has the least amount of energy. So let's just look at it a little bit more. So over here, we have one shell, one subshell in the first one, 2 subshells in the second one, 3 subshells in the fourth one, and so on. So over here we can see 1s has the lowest, then we go to 2s, 2p, which is the lowest, then 3s, 3p. However, there is an exception over here with 3d and 4s. The 4s orbit subshell has less energy than the 3d, so it's filled up before, which will look at how electrons are filled up. So let's just do some practice of how to write electronic configuration. Oxygen has 8 protons, and there must be equal amount of protons to electrons. So how do we do this? We know in the first shell there's only an s orbital. And how many can s orbital hold? S orbitals can hold 2 electrons. So we can say 1s2. Now we have 6 electrons left. Now again we go to the next shell, which is 2s2. So over here 2s2, and then finally we have how many electrons left? 4 left. If we go to the next subshell, which is 2p, and then there's 4 electrons to be 2p4. So this is the electronic configuration of oxygen. Now let's just try with another atom, magnesium. Magnesium has 12, so we know 1s2, 2s2, 2p6. How many electrons is this? This is 10 electrons, so we have 2 left. Now we're going to the 3 orbital, so we 3s2. Over here, now we're going to be looking at chromium. Chromium is an exception to this rule. It will go like 1s2, 2s2, 2p6. This is the first 10 electrons, 3s2. Now, what would you think? It will go to 3p6, right? So this is 12, so it'll be 3p6. So how many electrons is this? This is 18 electrons, right? And how many are left? 6. So you'd assume it would be 4s2 and 3p4, 3d4. But that is incorrect. Electrons will go, this is a very special case, when there's 5 electrons in a subshell, in the D subshell, it is more stable. So what would that mean? The 2 electrons which are originally going to the s orbital, only 1 will go, and one of those electrons will go to the d orbital to increase stability of chromium. The same is for copper. It will be the same thing till here, but it will be 4s1 and then 3d10. Since half-filled orbitals and fully filled orbitals are more stable. Now let's just look at orbitals. What are orbitals? So each subshell contains atomic orbitals, and it can be occupied by 2 electrons. So S orbital can have 2 electrons, P has 3 orbitals, so you can have 6 electrons, D has 5, so have 10 electrons, and we don't need to know about F, but it has 7 orbitals, so 14 electrons. So let's just look at the shape of orbitals, which you'll be told to draw. An s orbital always has the same shape. It can be drawn as a circle around the origin. So that will be the s orbital. However, as you learned, there's 3 p orbitals in each p subshell. So p can be in 3 different ways. We can draw it along the x-axis, which is over here. It's like an infinity sign. This would be px. Py can be along the y-axis, so like that. This is py, and pz will be on the z-axis, which is quite a bit harder to draw. So we'll draw a 3D grid over here, and it'll be just like that. That'll be PZ. So you can draw any of these shapes for the orbitals whenever it asks you to draw orbital of P. But however, this is the only S orbital which you must draw. And just as an idea, the further away you go, the increase in principal quantum number, the shells will get bigger. So the shell of S in the second principal quantum number shell will be bigger than that of the first one. Now let us look at energies of the subshell. So as you looked at, the electrons are filled from the highest energy. So we know 1s is the lowest amount, then 2s, 2p, 3s, 3p6, and then as you look at the exception, 4 has a slightly less energy than 3d, so it's filled up before the 3d shell. And all the orbitals which are in the same subshells have the same amount of energy. They're said to be degenerate. So all the orbitals and in the 3p, 2p, any of them have the same amount of energy as each other. So the other is greater. Now, let us do some practice. Let us do practice of oxygen 2 minus. This means there's a total of 10 electrons. So we know it will be 1s2, 2s2, and then there's we have 6 electrons left, which fits perfectly to 2p6. So this is the electronic configuration. Now, let's look at magnesium. Again, it will be 10 electrons, so it will be the same as oxygen, 2s2, and then 2p6. Now, iron and these transition metals are a bit different. Well, let's do the common 1s2, 2s2, 2p6, 3s2, and 3p6, right? So this is what? This is 18 electrons and we need 24. Now, we would remove from 3d orbital, you'd think, because this is the third orbital. However, this is wrong. You need to remove from the most energized or least energized orbital. So we'll have to remove it from the 4s first. So we have 4s2 before, and they're cancelled out because they're removing 2 electrons. So the only thing we have left is the 3d6. So that's how you do it for that. Just remember you have to remove the 4s electrons first, so they have less energy. So ground state. What is meant by the ground state? It is the most stable electronic configuration in which the atoms have the lowest amount of energy. So this is basically when it's filled from the slowest energy first, so 1s, and it goes up like that to 2s, 2p, like we saw in the diagram. Now, we need to learn about electron box rotation. So electrons are basically spinning charges, and they can rotate around their own axis. We don't have to worry about this too much. We just need to know there's a clockwise direction and there's an anti-clockwise direction of spin. So over here, we know P has 3 orbitals, so we've got 3 boxes with the notation. And the electronic configuration, just so we know, can be used instead. So over here, P has 3 orbitals, so we need to do we have 3 boxes. And there's just always a rule that always electrons are filled at first, and then when all the boxes are filled, then only electrons will start pairing. So if I have 4 electrons in the p orbital, we'll draw the 3 boxes over here. We would draw them by having 1 electron in each box first. So 1, 1, 1. And now there's 1 electron left, and we need to always have a different direction spin of electrons in each box. So the other electron will enter the first one again with the other direction spin. So you cannot have removed this one, and you cannot have this. This does not exist. It's always going to go to the next box first, and when all the boxes are filled, it will start adding again to that with the opposite direction of spin. So what are free radicals? So free radicals are species which have more than 1 unpaired electron. So over here you can see in chlorine that there's a 3p orbital and one of the boxes is unfilled. So this is known as a free radical. And the unpaired electron is basically shown as a dot. So I will write over here Cl and then a dot. That shows as a free radical. And free radicals are mostly formed in homolytic fission, which is basically when the 2 electrons of a covalent bond are split between 2 atoms, and it causes a homolytic fission, and it causes a free radical to form. So that is everything we need to learn about electronic configuration of atoms in CIE chemistry. If you guys have any question, please let me know, and I hope you enjoy.